Okay, so this is going to be section 1.2 and 1.3. 1.2 is going to be radians, arc length, and area. So let's get started. So radians is going to be a new measure for angles that we're going to be using as much as possible because it's a far better measure of how big an angle is than degrees. So the problem with degrees is that when you have it's arbitrary, basically. So a full circle is 360 degrees, right? Why is that? There's no scientific or mathematical reason for this. There is perhaps a practical reason that 360 is a very divisible number, right? So, for example, half of 360 is a whole number, 180. A quarter of 360 is a whole number, 90, right? 90 degrees. An eighth of 360 is a whole number, 45 degrees, right? So 360 is very divisible, so that if you're working with a lot of angles and you have a lot of people who perhaps aren't comfortable with fractions, then maybe degrees is okay, right? Just for that practical reason. The thing is, though, like I said, it's not scientific. It's not mathematical, right? Just as easily, we could have had a full circle be 720 degrees. It would actually be even more divisible than 360, right? Or we could have said a circle should be 100 degrees, right? Or 59 degrees, or 47 degrees, or 1026 degrees. So all of these, in a way, are equally as good as having 360 degrees in a circle, right? So again, degrees, it's very, very arbitrary, and so we need a better measure of angle that's more mathematical, right? And one that's more mathematical is going to be very advantageous to us when we actually start studying, for example, the trig functions. All right, so this more mathematical and more natural measure of degrees is going to be radians. So how do we measure radians? So the idea is if we take a circle of radius 1, right? Why radius 1? Because radius 1 is natural, right? It's the most, in a way, the most natural circle is just a simple one of radius 1, as opposed to, right, radius 29 or radius 1/3, right? Radius 1 is very natural, a natural size to be talking about. Okay, so I keep on saying natural because what I really want to emphasize is that the measure of this radians measure for angles is natural, right? One way you can think of it is if there were aliens and they came down to Earth and they had their own measure of angles, it's very, very likely, almost for certain, they would be using radians as well. All right. Okay. So let's say we have an angle. So let's say this angle here, put into standard position, right? So let's call this guy theta here. So how would we measure this angle in radians? How does the radians measure work? Well, very simple. So the radian measure of this angle, the size of this angle according to radians, is this length right there. Okay, so the radian measure of, I guess I should put the, theta is the length of this arc right there. Okay, so this is a very natural measure, and also it's kind of nice in that if you wanted to measure an angle in radians, you can just take out a tape measure, right? Take your angle, draw a circle, and use your tape measure to figure out how long that arc length is. And that's literally exactly the radian measure. Okay, so not only is it very natural, it's relatively simple in terms of the concept. All right. Okay, so if this is the measure that we use, what, for example, would be a full circle, an angle that goes all the way around? That would be let me draw it down here. If we went all the way around, again, this is a circle of radius 1. It's really important that it's a circle of radius 1 because a circle of a different radius, right? Let me draw a picture in the same picture here. If I used a circle of radius, let's say bigger, then if I calculated this arc length right there, it would be bigger, right? So it would not be the radian measure. Radian measure demands that you're working with a circle of radius 1. Okay. All right, so if I have a circle of radius 1 and I want to talk about an angle which in degrees would be 360 degrees, which in other words is an angle which goes all the way around. So here's the initial side, and then the terminal side is all the way around, so it's the same side. Okay, so this angle all the way around. What would its radian measure be? Well, it would be, again, literally the definition is the arc length of this arc right here, right? Well, in this special situation, the arc is actually the entire circle, right? So it's going to be arc length is, let me put this in quotes, entire circle, right? So it's going to be circumference of entire circle. Okay, oops. Okay, so what is the circumference of an entire circle? Well, the circumference of a circle is 2 pi r, right? But here, like we said, we're working with a circle of radius 1. So r here is 1, and so this is 2 pi. Okay, so in radian measures, the 360 degree angle is equivalent to 2 pi radians. Okay, so let me actually write that down. 360 degrees is equivalent, so 360 in the degree measure is the same as 2 pi in the radian measure. Okay, and radians, it's so natural that frequently we won't even use the word radians here. We'll just say 2 pi. All right, but if you did want to write kind of a descriptive word here, radians is often RAD. Okay. All right, but again, we'll often, very soon, we'll just be dropping the radian and just say we have an angle of size, for example, 2 pi, or size pi over 2, or pi over 7, or whatever. Okay. All right, so let's take a look at a few kind of basic angles, and let's see what their radian measures are, just to get a feel for this this new way of kind of sizing an angle. So what is a 90 degree angle in terms of radians? Is how many radians? All right. Well, again, the entire definition of the entire concept of a radian is we take a circle of radius 1, right? And I guess we don't need this part of it, so I'm just going to put it dotted. And we look at the arc length, right, that the angle creates. So this is our 90 degree angle. So this is the terminal side. That's the initial side. So the arc length we're talking about would be this arc length right there. All right. So it's going to be that length right there. And again, you could take out, this is so simple that you could take out a tape measure and measure this. But we already know that the full circle is 2 pi radians. And this is a quarter of a circle. So this is going to be 2 pi over 4, a quarter of 2 pi radians. All right. So it's going to be 2 pi. Let me write it as 1/4 of 2 pi radians. Because the arc is 1/4 of an entire circle. Okay, so in a way, the theme we'll see when we get to the latter parts of this section and even some of the next section, that the theme of today is to look at ratios. So here what we're saying is 2 pi is the entire circle, and we're looking at a quarter of that. Okay, so altogether 90 degrees is equivalent to pi over 2 radians. okay? Or just pi over 2, right? Because we'll be using more, we'll be kind of radians will be our natural measure. All right, what about 180 degrees, right? Same idea. 180 degrees is going to be, here's the initial angle, here's the terminal angle, circle of radius 1, like that, right? The arc that we're talking about is from here all the way to there. How long is this? Well, an entire circle is 2 pi. This is half of an entire circle, right? So this is equivalent to 1/2 of an entire circle, so it's pi. Okay, so 180 degrees is equivalent to pi radians. All right. Let's do one more. So what about 30 degrees? So 30 degrees is an angle that we're going to be working with quite a bit in our class, again, because trig functions work very well in terms of just simple computations with them. So here we're talking about a circle of radius 1. We want to measure how long this arc right there is. Oops. This arc, right? Here's our initial side. There's our terminal side. Okay. All right. Again, we can reason this out. We know that the entire quarter arc, right? So this quarter arc right there, this was pi over 2, right? 90 degrees. This 30 degrees is 1/3 of 90 degrees, right? And so this arc here has to be 1/3 of pi over 2. Okay. So we're in essence chopping up our quarter circle into 3 pieces, right? So this would be the 30 degrees, and then the next one would be 60 degrees, and then the next one would be 90 degrees. Each of these small wedges are 30 degrees, okay? So we've chopped up pi over 2 into 3 pieces. So each piece is 1/3 of pi over 2. And so 30 degrees ends up being pi over 6 radians, okay? So this is 30 degrees. All right, so maybe a good exercise is for you to pause right now and figure out 45 degrees, figure out 60 degrees, figure out 270 degrees, all right? Okay, so this is so far pretty straightforward, but we would like a general formula or a general method for conversion between degrees and radians, right? So for all the examples I've given, everything has worked out nice and clean just because everything has been a very kind of even cutting of the circle, right? So what about in general? So the idea here in general, so how to convert between our two measures, degrees and radians. So how do we convert between these guys for general angles? Well, the idea is to use the ratios, all right? So when we talk about an angle in terms of degrees, let me use this notation for this section here. So in degrees, I'm going to write, so let's say I have an angle theta here, all right? Let's call its measure in degrees, let me call it theta degrees. Okay, and let me call its measure in radians. I'm just going to call that theta. Okay, so for example, up above, we said this angle up here, right? We would call that theta degrees would be 30. Okay, and the radians would be pi over 6. All right. Okay, so if we think about ratios, theta degrees is a portion of the entire of the full circle's worth of angles, right? How much of a portion? Well, in total, a full circle has 360 degrees, and we're kind of considering theta degrees of them, right? So theta degrees over 360 kind of tells me how much 360 degrees. Let me put it like that. Tells me how much of the circle we're working with, right? A fraction of a circle that we're interested in. So in other words, if I draw a full circle here, right, This ratio here tells me, we're working with perhaps 1/8 of a circle for 45 degrees. We're working with 1/4 of a circle for 90 degrees, and so on. Okay, well, this guy here should be equal to the radian measure over 2 pi, right? Because radians, when we measure with radians, the full circle is 2 pi. Okay, so because no matter how we measure this circle or these degrees, whether in degrees or radians, these two ratios have to be the same number, right? Because both of these express how much of the circle we're considering, right? Again, with right angle, we would be considering on the left-hand side 1/4 of the entire circle. And we can see that it works. 90 degrees over 360 degrees is 1/4, right? On the right-hand side, we would be still looking at 1/4 of the circle. And that also works out in that we've seen 90 degrees in terms of radians is pi over 2. And pi over 2 over 2 pi is 1/4. Okay, so this formula has to always be true. All right, and again, the theme is that we're just looking at the ratios. The ratios have to match. Okay. All right, again, for another example, if I look at a straight angle, right, 180 degrees, then 180 degrees over 360 degrees, right, that should always be equal to the radian version, which is pi over 2 pi, right? So this guy on the left-hand side is 1/2. This guy on the right-hand side is 1/2, right? So indeed, they should always be equal, okay? So this ratio should always hold. And once we have this ratio, we're all set, right? Because if I want to convert from, let's say, degrees to radians, let's say I have an angle of 45 degrees, then this, let me do it in a different color here. This term right here would be 45 degrees, and then I can solve for the theta radians right there, okay? Or alternatively, if I had an angle of pi over 8 radians, then I would stick in a pi over 8 right there, and then I could solve for the degrees, okay? So we can relatively easily move between radians and degrees just using this kind of ratio understanding of degrees and radians. Okay, so in practice, for example, like I said, 45 degrees over 360 degrees has to be equal to the radian measure of 45 degrees over 2 pi, right? So what is this? Let's see, so this is going to be theta equals, so this is the same as theta equals 45 over 360 times 2 pi, which is going to be, maybe the easiest way to think about this is 45 times 2 is 90 over 360. And I know 90 over 360 is relatively simple. That's 1/4, so pi over 4. Okay, so this tells me, so 45 degrees is equivalent to pi over 4 radians. All right. And if you wanted to go the other way, if I had, let's say, pi over 10 radians, right? How many degrees would that be? I would stick in the pi over 10 radians right here, right, in for the theta radians, and solve for the theta, for the degrees. Okay, so theta degrees is equal to 360 times pi over 10 over 2 pi. Okay. All right. We can cancel the 2 and the 360, so 180 pi over 10 over 2 pi, like this. Oh, sorry, over pi. And this is how you, oftentimes, if you've seen trig before, this is how the formula is often written, where you're multiplying your radian measure, pi over 10, by 180 over pi. Okay, but I like to think of it with this ratio method because in a way you don't have to memorize two formulas, one for the radians, one for the degrees. You just have to understand one single formula and then you can move easily between radians and degrees. Okay. All right, in any case, if we simplify this, this is going to be, let's see, the pi's are going to cancel, the 180 and the 10 cancel, so this is going to be 18. All right, so we end up with 18 degrees. Okay, and so pi over 10 radians is the same as 18 degrees. Okay. All right. So a few of these maybe you'd want to do. Let's see. We've already seen 45 degrees is pi over 4, right? 30 degrees is pi over 6. 60 degrees is going to be pi over 3. And those are, let's say 90 degrees, pi over 2. These are ones that you should definitely know, basically immediately. But probably you don't need to sit down and memorize these because we're going to be working with these measures, these specific measures, 45, 30, 60, 90, so much that hopefully you'll kind of automatically commit to memory the pi over 4, pi over 6, pi over 3, pi over 2, and so on. Okay, 180 degrees is pi, 360 degrees is 2 pi. So those are a few of the important ones. Maybe let's stick in 270 degrees, right? So that's going to be 3 pi over 2. Okay, so let's actually use this new measure to calculate some things. So immediately we're going to have some nice applications. So arc length. This is our first application. So if I have a circle of radius, let's say r, all right, so now it doesn't have to be radius 1, any circle of any size. And let's say I have an angle here, right there, like this, of theta radians. Okay. So again, we're going to want to use radians as much as possible. So if I just say an angle of theta, and I just say, for example, theta is equal to pi over 7, then immediately that's radians, all right? So only when I say theta is equal to 27 degrees, when I use the word degrees, that's the only time we'll be using degrees, okay? So it's really important, for example, from here on out, that whenever you're working with degrees, for example, 27 degrees, to explicitly put the little circle, all right? Otherwise, if you don't, implicitly, we're always by default working with radians. Okay, so let's say we have an angle of theta here. So the question is, how long is this arc right there, right? So how long is, let me write it like this. What is the length of this arc? Okay. So this is going to be something very important for us. For example, when we talk about motion, circular motion, so perhaps something moving in a circular fashion around this circle here, then we're going to want to know, if we traveled 30 degrees, right, how, in terms of angle, how much does that kind of correspond to in terms of the actual distance that we traveled, all right? And that would be exactly the length of this arc, okay? All right, and the way we're gonna figure this out is again through the idea of ratios. So we're interested in this angle theta here, right? So how much of the circle does this theta represent? It represents, in terms of a fraction, right? It represents theta over 2 pi of the entire circle, all right? So what I mean is, for example, if this angle were pi over 2 or 90 degrees, then it would represent pi over 2 pi, which is a quarter of the circle, right? Which is exactly correct, okay? So this is how much the angle theta represents of the circle, all right? Well, on the other side, in terms of the arc length, how much of the entire circle does this arc represent? Well, if I call this arc length here S, so this is the notation that we're going to be using for arc length very frequently, S, okay? Then how much of the entire circle is S? Well, S over the entire circumference of this circle, all right? What's the circumference of the circle? Well, if it's radius r, then the circumference is 2 pi r. Okay, so S over 2 pi r represents, again, from a different point of view, the fraction of the circle that we're kind of working with. All right? So these two fractions of the circle that we're working with, they should be the same, right? One of them is representing a fraction in terms of angles. The other is representing a fraction in terms of the length of the edge of the circle, right? The circumference of the circle. But regardless, these two guys should be the same, okay? And so that gives us our formula for S, right? Because if I say, well, my angle is 45 degrees, then what is S, right? Then I stick in 45 degrees in here for theta. Again, in terms of radians, so 45 degrees would be pi over 4 radians. And then I would just throw the 2 pi r to the other side. Okay, so if theta is equal to pi over 4, then pi over 4 over 2 pi should be equal to S over 2 pi r, right? And so S should be equal to pi over 4 over 2 pi times 2 pi r, just throwing this 2 pi r to the left-hand side. Okay, and so we get a little bit of cancellation here, pi over 4 times r. All right. Okay, so again, what is that S? That's literally the length of this, let me draw it over here, the length of this arc right there. All right, so if you took out a tape measure, so let's say r was equal to 2, right? So this guy here would be 2. If you took out a tape measure, you drew a circle with size 2 here, and you measured this length right there, you would get pi over 4 times 2. All right, again, where this one here is pi over 4 angle, 45 degrees. All right. Okay, so that's the example for 45 degrees, but we can write this, we can write a general formula, right? So we had theta over 2 pi should be equal to, again, the ratio, this left-hand side is the ratio, the portion or the fraction of the circle we're interested in terms of angles. That should be the fraction of the circle we're interested in terms of arcs, right? So 2 pi r. And so this tells me S should be equal to, in general, theta over 2 pi times 2 pi r. And so that's going to be 2 pi's cancel, theta r. All right. Okay, I believe actually the book likes to call, in terms of the formula, the book calls the angle alpha instead. So if you look at the book, their formula will be S equals alpha r. But it's the same idea. The angle here is theta for me, and the book is calling it instead alpha. All right. Okay, so again, you can choose to memorize this formula, but I think it's better to remember where the formula comes from, because all you have to do is essentially remember kind of ratios. That's the key word, right? And then if you just remember this key word, you can kind of reproduce the formula from scratch. And so there's less chance of memorizing the formula incorrectly, all right? Okay, so let's do a quick check, right? Does this formula actually make sense, right? So what happens if my angle were the entire circle? My angle were 2 pi. Then what I should get for the arc length should be the entire circumference of the circle, right? Let's see if that actually holds. So when alpha is equal to, or when theta is equal to 2 pi, I get S is equal to 2 pi r. So when angle is 2 pi, so full circle, right? S, our formula tells us S should be 2 pi r. And that's correct, right? That's exactly the circumference of a full circle. Okay? All right, so this is just a quick check to see if our formula kind of makes sense intuitively. All right. Okay. So now at this point, you can calculate, given any angle, and any circle of any radius. So like this is the center. If I do that, I ask you what this arc length is, right? And I told you what this angle was, then you could calculate that arc length immediately. Okay. Now, one thing to note is that this formula only works in radians. So this alpha right here, or the theta, where I used it above here, that has to be measured in terms of radians. All right. You cannot stick in 45 degrees for alpha or for theta. That's not going to work because the way we kind of came up with this formula depended on the fact that we were working with radians, right? 2 pi r down here. Okay. You could come up with, using ratios, using the same idea of ratios, a formula in terms of degrees just as easily, right? That might be a good exercise to try out. Okay, so one practical application for this is if you have two locations on the globe, right, on the actual Earth. So location here and let's say a location here. Let's put this as the center of the Earth. Then let me put it here so that my drawing looks a little nicer. We can look at this angle right there from the center of the Earth to location 2, center of the Earth to location 1. Okay, we can draw this arc between them like that. Okay, we can calculate that angle right there. Then we can figure out from that angle and using our formula that we get the distance between our 2 points. All right, the actual practical distance, right? So if I were to walk from location 1 to location 2, this arc length right here would be the distance that I actually have to walk. Okay, again, this is in contrast to if I were able to tunnel into the Earth, right? Then I could tunnel through the Earth like that, and perhaps you would call that the distance. But in general, right, you can't tunnel through the Earth, at least in a practical sense. So when we talk about distance on the Earth, we're talking about, in essence, walking, or at least that's one way to think of it. And so this arc length would be the distance between the 2 points, all right, between the 2 locations, or between the 2 cities, or whatever it is on Earth. Okay, now one question you might ask is, how would I get this angle right here, right? I guess let me call it alpha. How would I get this angle? Well, that's a different issue, right? But in order to get that distance, you would have to figure out the angle. Later on in the class, we will be able to do this, but for now, not so much, unless these 2 cities are actually, or these 2 locations are actually at the same longitude, then we can calculate it. We know alpha because latitude is essentially the angle. All right. Okay, so that's arc length. Again, relatively straightforward if we think about it in the right way. Our next kind of mini topic is area of a sector. So we've got a circle. We want to figure out if we cut this circle, or let's say we have an angle that cuts this circle like this. Let me call the angle, I guess let me call it alpha, just to kind of stay with the book. All right. The question is, how much area does this angle cut out of the full circle? Okay. All right, so a practical, kind of a silly practical application here is if you want to cut a pizza into 8 slices, right? Then you know that 8 equal slices, let's say, then you know alpha, right? Alpha would be 1/8 of a full pizza, 1/8 of 2 pi. So from that, we can calculate how much pizza everybody gets, or how much pizza each slice is composed of. All right. Okay, so how do we actually figure this formula out? Well, exactly in the same way, right? So in ratios, again, if we're talking about an angle of alpha, then in terms of how much of the circle, what fraction of the circle does this angle represent? It represents alpha over 2 pi of the entire circle. Okay, and again, we're working with radians here. All right. Okay, Now, how much area have I shaded in here compared to the area of the entire circle? That fraction should be the same as alpha over 2 pi. Okay, and again, this ratio idea works because we're working with a circle, and the circle is uniform all the way around, right? And so this fraction on the left-hand side should be equal to the fraction, let me write down just the words area here, okay, area of sector, over the area of the entire circle, right? So area of entire circle. Okay, so these two ratios should be the same. What is the area of the entire circle? Well, that's going to be pi r squared, where r is the radius of our circle. Okay, so I guess I should note here, that would be my radius, right? So that's getting a little messy. Let me rewrite it down here again. Alpha over 2 pi should be equal to the area of the sector, so what we're actually looking for, over pi r squared. Okay. All right, so if I want a general formula for the area of a sector, in terms of the angle, I can throw the pi r squared to the left-hand side, right? So area of the sector is equal to alpha over 2 pi times pi r squared. And so here the pi's are going to cancel. So I'm going to get alpha r squared over 2. Okay. So this is the formula that you would see, for example, in our book. Okay. And again, you can memorize this formula if you like, but I prefer to kind of understand where it comes from, because it's really, really easy to memorize a formula incorrectly. But if you kind of figure it out from the basic idea, the basic principles, it's much easier to kind of get it correct. All right. Okay, so let's see if this again makes sense. If our angle alpha is all the way around, right, the entire circle. So if alpha is equal to 2 pi, right, in other words 360 degrees, then area of the sector should be the area of the entire circle, right? So pi r squared, right? So if our angle here alpha were the entire circle, then the shaded region should be all the circle, right? And let's check our formula for this special case, right? So our formula says alpha r squared over 2. That's going to be, well, alpha is 2 pi, so 2 pi r squared over 2. That's pi r squared. So it looks okay, all right, in this special situation where alpha is the entire circle, all right? And this is actually, you can kind of use this as a quick check of your formula if you are, for example, going to memorize it, right? Make sure that it's correct for the entire circle. Okay, but again, this formula allows us to move between the angle to the area of the sector, but you can also move the other way around. If I give you the area of the sector and the radius, you can figure out the angle. All right. Okay, and again, always want to emphasize, this formula only works in radians because, for example, this, you can see this left-hand side here where I got the formula from, that was entirely in terms of radians, right? The alpha is in radians, 2 pi is in radians. If you stick in alpha in terms of degrees, this ratio here is not going to be the correct fraction of the circle that we're interested in, all right? In fact, that indicates that if we want a formula in terms of degrees, one way we could figure that out is whatever your degrees is, whatever your angle is in degrees, right? The fraction of the circle you're interested in should be out of 360, okay? All right, so like I said, now you can figure out the area, area of, let's say, an 18-inch pizza with 8 slices, right? Area of, that doesn't really make sense. Area of each slice of an 18-ounce pizza that's been cut into 8 slices. All right. Okay, by the way, if you are going to calculate this, I guess in practice, an 18-ounce pizza is usually, like if you actually go out and buy a pizza, the 18-ounce pizza is actually the diameter, right? So the radius would actually be 9. All right, so that's our section 1.2. And again, our theme was to use ratios to understand different geometric aspects of a circle. And again, all of this was done through using radians. So be very, very careful with your formulas. You don't want to plug in degrees into a formula that's natively in radians.